Hello everyone, I'm Dinesh from CSCA department and this is my BWG presentation. And the topic is Kirchhoff's third and fourth laws. And the topic covered is Kirchhoff's third and fourth laws. Topic learning outcome. Okay, from this topic we can understand Kirchhoff's third and fourth law briefly. From this TikTok BWG presentation, we will know about Kirchhoff's third and fourth laws, graph theory, and calculations of Kirchhoff's third law and calculations of Kirchhoff's fourth law. Introduction. Symbolic analysis for analog circuits has received quite some research interest over the last 10 years. In numerical simulation, the values of all circuit elements are given and the circuit response to an input excitation is calculated in numerical form. In symbolic computation, the circuit elements are represented by symbols and the desired network characteristic is derived in infinite terms or in physics language as an analytic expression. This paper focuses more particularly on the symbolic computation of network functions of linear passive circuits. The computation of network functions in symbolic forms is a starting point for tolerance analysis, fault diagnosis, behavioral model generation, statistical circuit analysis, optimization, and the associated calculation of component values. In brief, symbolic computation can be very useful in all applications which involve the repeated evolution of circuits characteristics. This paper proposes an implementation in Maple language of the computation of any network functions E by I, E by E, I by E, I by A of linear passive circuits by means of the so-called Kirchhoff's third and the fourth laws. These laws allow one to express network functions in a very concise way in terms of trees enumerations. The symbolic computation of network functions is closely related to the computation of the inverse of a nodal admittance matrix. Both of problems are effectively solved by tree enumeration methods. Sections 2 recalls Section 2 recalls some definitions of graph theory which are necessary to understand the statement of the Kirchhoff laws. Section 3 and 4 give the statement of the third and the fourth Kirchhoff's law. The proofs of these laws can be found in 4 with minor corrections 3. Two-hand calculations of these laws are detailed on section 5 and 6. Finally, section 7 and 8 presents the algorithm and propose a practical implementation of the Kirchhoff's third and fourth laws. Graph theory. Some definitions of graph theory are recalled in this section. The terminology is standard except for the terms split tree and co-split tree. These new terms are proposed by the authors to give an uniform statement of the third and fourth Kirchhoff's law. Graph. A graph or network consists of a set of nodes together with a set of edges that connect the nodes. and this is the graph. Tree. A tree is any set of edges that connects all the nodes but doesn't form any loop. Code tree. The code tree of a tree is its complement, that is, the set of all edges of the graph that do not appear in the tree. This is tree and code tree. Loop. A loop is any set of edges that forms a closed path. For loop. The for loop of a loop is its complement, that is, the set of all edges of the graph that do not appear in the loop. Loop and for loop. Okay. Split. Split tree. A split tree, split into trees, is any set of edges whose removal would disconnect a graph into two trees. Co-split tree. The co-split tree of a split tree is its complement of the remaining two trees, that is, the set of all edges of the graph that do not appear in the split tree. Split tree, co-split tree. The definition of a split tree must not be confused with a cut set, which is a set of edges whose removal would disconnect a graph. Similarly, the definition of a co-split tree must be confused with a two tree, which is a set of edges obtaining by deleting an edge from a tree. Kirchhoff's third law. Given any connected resistance network G, if a voltage generator EI is inserted in a branch RI, then the current IK through any branch RK is given by equation 1. And that are the equations 1 and 2 and 3. How to read the expressions of D? The summation is carried out overall the code trees of the network. The term is the summation is the product of all edges resistances of a code tree. How to read the expression of N? The algebraic summation is carried out over all the loops that include as its edges both RK and RI. The associated sign of the term is positive if the directions of IK and EI along the loop are in the same sense. A term in the summation is the product of all the edges resistances of the associated co-loop. Kirchhoff's fourth law. Kirchhoff's fourth law. Given any connected conductances network G, if a current source IL is placed across any branch GI, then the voltage EK across any branch GK is given by equation 5 by equation 4. That are the equations 4, 5 and 6. And next, how to read the expression of D0? The summation is carried out over all the trees of the network. A term in the summation is the product of all the edges conductances of a tree. How to read the expression of N0? The algebraic summation is carried out over all the split trees that include as its edges both GK and GI, and so that GK and GI connect the two trees. The associated sign of a term is positive if the direction of EK and IL connecting the two trees are in the same sense. A tree in the summation is the product of all the edges conductances of the associated two trees. Co-split tree proceedings. Hand calculations of Kirchhoff's third law. The third Kirchhoff's law is illustrated in the network shown in figure 1. We want to express the current I phi through the resistance R phi in terms of the supply E0 and the given resistances. And that is the figure 1 bridge resistance example. All the subgraphs that contain edges 0 and phi and possessing one loop are shown in figure 2. And this is the figure 2 loops of network. The respective co-loops of the previous subgraphs is given on figure 3. The trees and their associated co-trees are given in figure 7. And by 8 and 8. By inspection of subgraphs on figure 2, 3 and 8, the current I phi is like this. I phi equal to R2 R3 minus R1 R4 by R3 R4 R5 plus R2 R3 R5 so on R0 R1 R3 into E0. And calculation of Kirchhoff's fourth law. The fourth Kirchhoff's law is illustrated in the network shown in figure 4. We want to express the voltage E phi across the resistance R phi in terms of the supply I0 and the given conductances. And that is the figure 4 bridge conductance example. All the subgraphs composed of edges whose removal would split the graph into two trees linked by edges 0 and phi are shown in figure 2. Okay, that is the figure split trees of network in figure 4. The two remaining trees of the previous subgraphs are given in figure 6. Edges 0 and phi are represented in dashed line for clarity. And figure 6 co-split trees of network in figure 4. The trees and their associated co-trees are given in figure 7 and 8. By inspection of the subgraphs of on figure 5, 6 and 7, the voltage E phi is equal to G1 G4 minus G2 G3 by G0 G1 G2 plus G0 G1 G4 plus so on G2 G4 G5 into I0. And the conclusion. The conclusion is the unrecognized Kirchhoff's third and fourth laws have been recalled in this paper. These laws allow one to compute network functions of linear positive circuits in state formulas. The statement of these two laws have been detailed as they are stated as they are stated in a formalism which is unusual to most scientists from the electronics community. A very concise maple programs to compute them have been proposed. And thank you. And my PPT on BWA has completed. So, thank you.